Hey there, everybody. Welcome back. This is Calculus 3. We are in 15.3 of Anton's 11th edition book. This section is on conservative vector fields, and we are looking at the conservation of energy principle. So we're going to start with F is a conservative vector field. It's the gradient of some potential function phi. Then we will call V, a function V of x, y, z equal to the negative potential function, or the potential function. So V will be the potential energy of the field at P. Thus, the work done along C, if we do the line integral along C of F dot dr, we get the work. It's phi of P1 minus phi of P0. And that's going to equal, if we plug it, treat this in terms of like move the negative over. These are negatives. It just makes the whole thing negative when we change it to V. So what is this? This is a change in the potential, a negative change in the potential energy. The work done by the field is the negative change in potential energy. Okay. If it's piecewise smooth, closed path, W equals 0, no change in potential energy. But if this is a particle of mass M with initial speed UI and a final speed UF, the work done on the particle is, from physics, 1/2 mv squared. V here is UF and UY. So 1/2 MUF squared minus 1/2 MUI squared. That's got to be our change in our potential energy. Negative F V of F minus VI. So this one is the kinetic energy from the first part, or the final. Initial kinetic energy, final potential energy, initial potential energy. Sorry, I got a bad tickle in my throat. And these are velocities, U, F, UI, these are velocities. I didn't use V because we have V over here. What we're going to do is we're going to move all the things with an F subscript to the left, all the things with the I subscript to the right. We're collecting them by time. I have 1/2 MUF squared plus VF has to equal 1/2 MUI squared plus VI. This is the kinetic energy and potential energy on the left, or the final kinetic energy and potential. And we see that equals the initial kinetic energy and potential energy. They must equal some constant value because they equal each other. Since there's no change in the sum of these two, energy is conserved, nothing is lost, nothing is gained. That's what conserved means. You haven't lost or gained anything. So the sum of the kinetic energy and potential energy is constant as a particle moves along a path in the conservative vector field. That's actually why we call it a conservative vector field. This is called the conservation of energy principle. And it's why we call the vector field conservative, because it conserves something. You will see that in other things. Oh, this is real fun, real quick. Let's just bring up the Navier-Stokes equations. NASA's usually got a good one. I like the NASA's one best. Where is NASA's? There we go. Conservation of momentum equations, conservation of energy, and continuity. They're all conservation equations. The laws that govern fluid dynamics and some of the hardest mathematics on the planet are all conservation principles. That's it for 15.3. Peace.